Is the person in the mirror really you? They make the same movements and expressions as you. But are they truly identical? The truth is, not completely. This isn't philosophical speculation, but a scientific fact that has been experimentally verified and is groundbreaking. Hello, Earthlings. Welcome to Oldma's Mystery Club. In the past, everyone firmly believed that the laws of physics were perfectly symmetrical. Like looking in a mirror, the world inside and outside the mirror follows the same rules. This is known in physics as parity conservation. It was once the iron law of the entire field. Until 1956, when two young Chinese scientists stepped forward and made the astonishing claim that in the microscopic world, parity is not conserved. The weak nuclear force is a left-hander. It favors the left side. But is the universe truly left-handed? This prediction, so bold that the entire physics community dared not believe it, came from Chen-Ning Yang and Tsung-Dao Lee. Just 1 year later, physicist Chen-Xiang Wu, using a cryogenic experiment with cobalt-60, confirmed that the universe is left-handed. This theory transitioned from a hypothesis to a scientific fact. In 1957, Yang Chen-Ning and Tsung-Dao Lee quickly won the Nobel Prize, making history. Yang Chen-Ning was only 34 years old at the time. The theory of these two Chinese scientists, using experiments, tore apart the decades-long belief in parity conservation. In physics, in the physics community, there is a view that the three major milestones of 20th century physics are Einstein's theory of relativity, quantum mechanics by Dirac and others, and Young's gauge field theory. Freeman Dyson even stated bluntly that Chen-Ning Yang was the distinguished architect of 20th century physics, following Einstein and Dirac. This praise is not an overstatement. In the physics community, the core criterion for judging a theory's value is its unifying power. Maxwell's equations unified electromagnetism. Einstein's theory of relativity reshaped our view of space and time. Young's work, on the other hand, laid the cornerstone for half of modern physics. His research spanned particle physics, field theory, statistical physics, and many other fields. Each breakthrough would be enough to put an ordinary scientist in the history books. What's more special is that he broke the prejudice in the Western scientific community regarding the ceiling for Chinese researchers. As Chen-Ning Yang once said, "The most important contribution of my life was helping the Chinese people change the mindset of feeling inferior to others." This spiritual awakening is far more significant than a single scientific discovery in nourishing a nation's soil for innovation. Among Yang Chen-Ning's scientific contributions, there are three achievements that stand out as pinnacles of human intellect. Collectively form the core framework of modern physics. First is parity non-conservation, tearing apart the universe's mirror illusion. Simply put, the universe loves symmetry. Like when you look in a mirror, you raise your left hand, and the person in the mirror raises their right. The movements and appearances are perfectly symmetrical. This is parity conservation. In the past, physicists firmly believed that the microscopic world was also like this. The mirror image of a particle would follow the exact same laws of motion as itself. This was the iron law of physics. But experimental data showed inexplicable contradictions. Then, in 1956, he and Tsung-Dao Lee discovered that in the weak nuclear interaction of the microscopic world, a special kind of microforce, the mirror was broken. To give the most common example, imagine a microparticle as a rotating small magnet, like cobalt-60 in Chen-Xiang Wu's experiment. When it decays, it releases marbles or electrons. According to conservation, these marbles should fly uniformly in all directions, front, back, left, and right. But in the experiment, They surprisingly flew concentratedly in one direction, and the direction of flight in the mirrored magnet was different. Simply put, the universe is not ambidextrous. It is a left-hander that favors one side. So what is the significance of parity conservation or non-conservation? Simply put, if the universe were perfectly symmetrical, matter and antimatter would have long canceled each other out. There would be no Earth or human beings. It is precisely this asymmetry that allows us to exist, and this directly paved the way for the later standard model of particle physics, which is the core theory explaining the microscopic world. Even the Nobel Prize rushed to endorse it. It is also one of the fastest verified discoveries in Nobel history. However, parity non-conservation is only the second most dazzling pearl on Yang Chenning's scientific crown. His most important contribution in his life was the one he proposed in 1954, the one that sounds more abstract, Yang-Mills gauge field theory. What is this field theory used for? You've heard of the grand unified theory, right? And the work of Young and Mills took the most critical step towards that dream. Don't be fooled by this abstract name. Simply put, it is essentially a universal rule for the forces of the universe. You can think of the forces in the universe, such as electromagnetism and the strong force that holds atoms together, as different courier companies. In the past, each company had its own delivery rules, which physicists had to study separately. It was very troublesome. What the Yang-Mills gauge field theory did was to establish a set of universal courier rules. Whether it's the electromagnetic force, the strong force, or the weak force, all can be uniformly explained by the logical operation of this single set of rules. This is equivalent to building a common bridge for different forces. Today, this theory has become the universal language of modern physics. The Large Hadron Collider detecting the Higgs particle, modeling the early universe's energy, and even the theoretical foundation of quantum computing all depend on the Yang-Mills equations. According to statistics, there are 7 Nobel laureates directly based on this theory, and dozens more are indirectly related. Even the Fields Medal in mathematics has been repeatedly awarded to scholars studying this equation. The U.S. Bower Award praised it, stating that it stands alongside the achievements of Newton, Maxwell, and Einstein, and will have an equal impact on the future. We can say that at least 2/3 of our current understanding of the microscopic world is built upon his theory. This is the most precious scientific legacy he left to all of humanity. Third is the Yang-Baxter equation. This is a bridge connecting physics and mathematics. This one is quite interesting. You can imagine microparticles as people standing in a queue before rules were set. If two people swapped places, the overall order of the queue could easily be disrupted. In the 1970s, what the Yang-Baxter equation did was to set a rule for particles to exchange positions. No matter how particles exchange positions, the mathematical order of the entire microscopic system will not be disrupted. Just like people in a queue swapping places, the line remains orderly and confusion-free. In the past, physics and math research often proceeded separately. This equation, however, connected them. Physics needs it to explain particle laws, and mathematics relies on it to find new research directions. It even helped mathematicians win the Fields Medal, hailed as the Nobel Prize of Mathematics. The quantum computers people often talk about today are most afraid of data becoming corrupted during computation. The topological qubits supported by this equation can make quantum computing more stable and accurate. It is a crucial foundational tool for quantum technology. Simply put, it solved the difficult problem of how the system maintains mathematical consistency after particle exchanges. It's like a set of exquisite cosmic calculation rules It is not just a physics equation. It is a paradigm of using physical problems to drive mathematical progress and then using mathematical tools to feed back into physics. Even now, whether building quantum computers or calculating cosmic models, it is indispensable. It's like a bridge that allows the wisdom of physics and mathematics to flow between each other, continually building ladders for human technology. However, a cruel reality is this. Even a brain such as his could not break the limits of human lifespan. Just today, October 18, 2025, Mr. Chen-Ning Yang passed away in Beijing at the age of 103. When we review Chen-Ning Yang's century-long life, we discover a thought-provoking fact. His most important gauge field theory was proposed at 33. Parity non-conservation was discovered at 35, and the Yang-Baxter equation was born at 46. Even with his longevity, he admitted in his later years that his experience could no longer support cutting-edge deductions. If we look back at history, we must confront a brutal proposition. Is the limit of human lifespan hindering the speed of scientific progress? Look at Einstein, who died at 76. Bohr, 77. Maxwell, 48. Newton, 84. Here we can't help but make a hypothesis. What if the flame of life for these scientific giants could burn for 200, 300 years, or even longer? If Einstein had more time, Bohr could have personally witnessed the birth of the quantum computer. If Mr. Chen-Ning Yang's theories could have been personally advanced by him into a more profound future, would the human scientific revolution have been an explosive leap forward? Would we have mastered controllable nuclear fusion sooner, achieved interstellar travel, uncovered the secrets of dark matter and dark energy, thereby entering the ranks of a higher-level civilization? The brevity of life is perhaps one of the biggest drawbacks to civilizational progress. We have barely gained our footing on the shoulders of giants. Before the giants have quietly passed away, in his later years, Chen-Ning Yang once said, "Scientific exploration is like building blocks in the dark. Some build the foundation, some add the pillars, and lifespan determines how many blocks each person can build." Now the giant has departed, and the starry sky of science is missing a colossal star. But the forest of theories he planted continues to grow, perfectly illustrating what passing the torch truly means. He returned to China in his later years, rooted himself in Tsinghua, and dedicated his lifelong wisdom and vision to his homeland's scientific cause. He dedicated himself to nurturing the next generation of scientific sparks. Although the palace of physics is missing a great master, but the seeds of wisdom he sowed have spread globally. He made us believe that the universe's mysteries can be rationally explored, and that human wisdom can touch the blueprint of God. Today, we remember Mr. Chen-Ning Yang, not only as a great scientist, but also as a spirit of exploration, a dignity of intellect, and his deep affection for his homeland, and all humanity rooted in his bloodline. Rest in peace, great master. His thoughts live on,